So to state the fourth isomorphism theorem, it's usually stated by saying that there's a one-to-one correspondence between two collections, but that tends to always be cumbersome the first time you see it, so I'm going to differ from the book and state it, the two collections, as using set notation. So let K be a subgroup of G, then S of Kg is going to be the set of subgroups of G with the property that K is a subset of H. So subgroups H, so K is a subset of H, which is a subset of G. So S stands for subgroup. So it's the subgroups that lie between K and G. N stands for normal subgroups, so N of Kg is those subgroups that are where H is normal at G. Then the fourth isomorphism theorem is the following. Suppose you have a normal subgroup of G. Then there exist bijections, phi, I'm going to call them both phi, between the subgroups that lie between N and G, and all subgroups of the quotient group. So in other words, every subgroup of the quotient group, for all H a subgroup of the quotient group, this means that there exists a K subgroup of G with N a subset of K, and K mod N equal to H. That's what that part is saying when you're saying that this is a bijection. So all the subgroups of the quotient actually must be quotients of subgroups over here, and vice versa. Similar here, the difference is now you're talking about normal subgroups. And more importantly, distinct subgroups come from distinct subgroups, and distinct subgroups map to distinct subgroups. So here we are going to apply the fourth isomorphism theorem. And the group we're going to work with is S4, the symmetric group of all permutations on four symbols. One through four. Remember there are 4 factorial permutations, so 24. And I'm going to let N be the subgroup consisting of these permutations. This is a normal subgroup. One way to see that is to remember that when you conjugate a cycle, the result you're going to get is sigma A, sigma B. And so when I conjugate one of these disjoint 2 cycles, if you're clever, you can insert a sigma inverse in the middle, and get that the result is also going to be a permutation with 2 disjoint 2 cycles. Why? Because each of these 4 entries is going to have to be distinct. And so the point is when you conjugate one of these permutations in this subgroup, you're going to get another permutation that consists of exactly 2 2 cycles. And these are all the permutations with 2 2 cycles. So you're going to get another permutation in this set. And so we see that sigma inverse tau sigma is in N for all tau in N and for all sigma in S4. So in fact, this is a normal subgroup. By Lagrange's theorem, it has size, the corresponding quotient group has size 6. And so you can check that it turns out one set of coset representatives is given by this. The transposition 1, 2, the transposition 1, 3, the transposition 2, 3, and the 2, 3 cycles. Just looking at what you have, you can clearly see that these representatives are all permutations of 3 symbols. And so it turns out this group, this quotient group, is actually S3. So the point of the fourth isomorphism theorem is that there's a bijection between subgroups of S3 and subgroups that lie between this normal one and all of S4. So if you're trying to classify all subgroups of S4, having this normal subgroup simplifies your problem a little bit, because now you can look for all subgroups in between N and S4. And then you look for all subgroups that avoid N entirely. So what are the subgroups of S3? Well, there's the trivial group, the full group, and then there's these groups of order 2. And one group of order 3. This particular group here is actually normal in S3. So by the fourth isomorphism theorem, this is going to correspond to a subgroup in S4 that is normal. It turns out you can check it ends up being A4. You can check that 1, 2, 3, N and 1, 3, 2, N. The union of these two cosets is the set of all 3 cycles in S4. So that's something you can check. That's actually kind of interesting. Now what about these other examples? Well then what you get is that N union 2, 3, N is a subgroup of S4. Similarly, N union 1, 3, N. And N union 1, 2, N. So as an example what these groups look like, I will point out that the coset 1, 3, N ends up having 1, 3 in it. The 4 cycle 1, 2, 3, 4. 2, 4, and 1, 4, 3, 2. And so when you combine this with N, which has 1, 2, 3, 4, 1, 3, 4, 2, 4, and 1, 4, 2, 3, it turns out you get a dihedral group. You can check. You have the rotation clockwise, the counterclockwise rotation, the 180-degree rotation, the vertical flip that sends 1, 2, and 3, 4, the horizontal flip that swaps 1, 4, and 2, 3, this diagonal flip that only swaps 2 and 4, The other diagonal flip that only swaps 1 and 3. And that's the identity permutation. So you do get a dihedral group there. And that is from 1, 3 here. The symmetry group of this labeled square. Oddly enough, the other two also end up being similar permutation groups, but they involve different labelings of the square. So remember correctly, this one ends up corresponding to what happens if your group member accidentally screwed up and swapped the 3 and the 2. Because 1, 2, n ends up having 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. And so you start to see these are the clockwise and counterclockwise rotations. They just look a little weird because you've labeled the square incorrectly. Finally, the other interesting coset is this one. 2, 3, 1, 3, 4, 2, 1, 2, 4, 3, 1, 4. You see that you end up getting what happens if a person screws up the labeling of the bottom edge. Instead of labeling it clockwise, they label it linearly. And so these 3 different ways of labeling a square give rise to 3 different permutation groups that are all isomorphic to D4. But they're all proper subgroups of S4. And the way we found them was by applying the 4th isomorphism theorem and just looking at subgroups of the quotients, the subgroups of S3. Which is good, because actually finding these subgroups directly probably would have been hard.